Dr. Rahul is currently a postdoctoral researcher at the Department of Structural Engineering and Building Materials at Ghent University in Belgium. He completed his master's from National Institute of Technology, Karnataka, and his doctorate from Indian Institute of Technology. He has also worked as an assistant professor in the College Federal Institute of Science and Technology in India.
Yeah, so as was introduced by the speaker, I'll be giving a small lecture on concrete 3D printing and concrete 3D printing within the context of sustainable construction. So this will be the outline of my presentation. We start with understanding what is concrete 3D printing, how is it different from a conventional method of construction. Then we look at the material requirements for concrete 3D printing, the material requirements in terms of three aspects. One, the early age or the fresh behavior of printable concrete, how it has to be fine-tuned for 3D printing application. Then we talk about its mechanical behavior. Then we also do a limited discussion on long-term performance. There isn't too much literature on long-term performance of printed concrete, this being a relatively new technology. But based on some of the literature that's already published, what we can understand of its long-term performance is also something that I will talk about in this lecture. Then after that, we look at the main, we try to answer the main question from this presentation: is concrete 3D printing sustainable? Or what is the way in which this technology can be used for sustainable construction? Then we summarize the presentation, and then we look at the research needs or the way we need to move forward to bring up this technology. So we start with what is concrete 3D printing. Some of you must have seen already videos of how concrete 3D printing works. So concrete 3D printing is a method in which structure is formed by the layer-wise deposition of a special type of concrete. This is quite evident in this image here. You can see that the structure consists of different layers, and these layers are deposited through a print head or a nozzle. And the motion of this nozzle is controlled by a gantry-based 3D printer, or sometimes using an industrial robot also. And the element or the structure to be made is first made as a 3D CAD model, a virtual model, and then this is fed into the system, which is then made to move in a specific direction so that the particular structure can be fabricated. So here you also see a column being made, and here you see a uniquely shaped structure being made by concrete 3D printing process. So just to summarize how the technique works, first we create a virtual model. Then the virtual model is used to create an STL file. The STL file essentially generates the instructions for the printer, which is called G code, which forms the instruction for the 3D printer, which then moves in the required pattern to create the physical object. Then the question comes, why do we need to adopt this technology? What is the advantage of doing this technology? Now, one of the advantages is the speed with which the construction can be carried out. This, if you go back in this figure, you see the column here. This was made in our university here. This is about 2 meters high, this column. And this column was made in a very short duration of around 10 minutes. If you compare it with how this column would have been made through conventional construction, you would first need to make a formwork for this column, where you would need to deploy resources to set up the formwork. So this takes up time, this takes up resources. But when you compare it with this method of construction, where you do not require a formwork, there's a significant increase in the speed with which you can have the structure constructed. The formwork free, as I said, is the other advantage. Geometric and design flexibility. Now, this is a very important aspect that we need to understand in context, especially in context of sustainability, which we will discuss in detail in a later part of this presentation. Just to give you an idea what this means is the shape freedom that you can have with concrete 3D printing, because you don't require to make customized formwork for uniquely or shape optimized structures. All these unique shape structures, as you see here, are actually possible through concrete 3D printing without a significant increase in cost, because you don't require a customized formwork to have this particular structure fabricated. So that these essentially makes up the advantages of concrete 3D printing. How has been concrete 3D printing looked up around the world? The first idea of concrete 3D printing happened in the late 90s. So the idea that construction can in fact adopt 3D printing like it's being adopted in the other industries, like for example, automobile industry, for example, a lot of their manufacturing or assembling happens in an automated manner. So there was a talk about if we can introduce automation in construction, what advantages we can gain from that. This idea was essentially postulated in the 90s, but the real proof of concept of actually a concrete being designed for 3D printing application, a real more like a proof of concept, although demonstrated in a laboratory, came in the US around 2012, and also in the Loughborough University around about at the same time, Loughborough University in the UK. So this happened somewhere around here. Before that, there was again some more of ideas being put up of how this technology could work, but not really like a proof of concept. Once the proof of concept was demonstrated that this is indeed possible, a lot of people then started to look at this technology. It kind of exploded, as you can see here. A lot of research groups around the world is now really looking to harness this technology and how we can really employ 3D printing in construction. If you see major research groups in the US, even a lot of research groups in Europe here as well, a lot of people are looking at concrete 3D printing. Asia also, China is very progressed in concrete 3D printing. Singapore is also one of the main players in concrete 3D printing from Asia. India, IIT Madras, for example, is continuing its research on concrete 3D printing. There's also a startup company which recently built a house in India by concrete 3D printing. So a lot of research focuses now on concrete 3D printing, realizing its advantages. But then when it has advantages, it also has certain hurdles that has to be, we have to go past these hurdles to really make full potential use of this technology, which again, we will look at it at a later part of this presentation. So I'll also just talk about some of the major 3D printing projects happening around the world, or how the industry has embraced this technology. So one of the construction that stands out is a barrack building, which is the result of the research by the U.S. Army Corp. The interest of U.S. Army Corp in concrete 3D printing is to really look at construction in hostile areas, or where it's difficult to transport labor or construction equipments and deploy that many resources for making a facility. So here they use concrete 3D printing with limited labor. They're able to construct these structures in inaccessible regions. So, for example, a barrack building made by the U.S. Army Corps is shown here. Then structures that show the real architectural freedom that you can have with concrete 3D printing. For example, these houses made in Netherlands are examples of this. If you see here, then there are also differences in the way concrete 3D printer itself has been used. For example, this pavilion construction in France uses on-site 3D printer. So a mobile robot is moved to the construction site, and then it is used to deposit concrete at different places to form these structures, as you see here. Then there are also some significant concrete 3D printing construction happening in Dubai as well, which is shown in this image here. Yeah, so with having given a background into what concrete 3D printing is, now we look at the material requirements for concrete 3D printing. We start with understanding its early age behavior. Now, as you see in the images that I showed you earlier, unlike a normal concrete which flows out which doesn't retain its shape once it exits the pump, or once it's deposited in position, it's unable to retain its shape, and you require a formwork to support it. So this concrete that we use for 3D printing has certain characteristics that allows it to retain its shape. So how can these characteristics be achieved is something that we'll talk about briefly in this section. So just to give you some introduction to just to introduce to some of the terminologies as well. Now, for any material to be used for for 3D printing, not just concrete 3D printing, even say polymer 3D printing, it's the key aspect that you need to work with is to achieve a solid to liquid-like or a liquid to solid-like transition. For example, if you're using polymer for 3D printing, which is very popular now, you melt the polymer to above its melting point so that it flows like a liquid while it's being pumped. And then at the point where it's deposited, it's immediately cooled down so that it undergoes a transition to a solid-like behavior, it has solid-like characteristics. And this then allows it to maintain its shape once it's deposited. So that liquid to solid transition at the print head is a key element for 3D printing to work. The same applies to concrete, but how is this done in concrete? We will look at that in detail. The ability of the concrete to be pumped up to the print head, we call that as the extrudability, or the ability for the printable concrete to be pumped until the nozzle. This term that we call as extrudability. And then once it's extruded from the nozzle, the ability for it to retain its shape, the fact that you can build one layer above the other, is what we call as buildability. So these two parameters are two critical parameters that we need to assess for developing 3D printable mixes. Now, before we understand how concrete can be designed for 3D printing, I'll also give you some basics about the rheology of concrete, or how concrete behaves as a fluid. And now, as you all know, if you look at solids, for example, a pure solid, and if you apply a shear stress on the solid, and if you measure the shear deformation, you can write out this relationship. If it's an elastic solid, that the shear stress is proportional to the shear strain. And the proportionality constant, we use a modulus to denote the proportionality constant. This is true in the case of an elastic material. If you do this in the case of a liquid, what happens is that the liquid is unable to resist shear. So in fact, you write a relation in terms of the rate of shearing of the liquid when a particular shear stress is applied. And the rate of shearing, the proportionality involved in the relationship, is what we call as the viscosity of the fluid. And then there's also viscoelastic response, which is an intermediate response between the two. Now, if you look at how a typical liquid behaves and how concrete behaves, say, for example, if you plot shear stress versus shear strain, as you see here, this is how you denote a Newtonian fluid. So as you see here, a Newtonian fluid, so this would represent the equation of a straight line with y-intercept is equal to 0. So as you see here, it passes through the origin. So even if you apply a very small amount of shear stress, you see a strain rate, or the material being sheared at a particular rate, which then allows you to plot this graph. But if you do this in the case of a solid, you will, in the case of a material like concrete, you will see that you end up with a non-zero y-intercept. And the non-zero y-intercept, which we call as tau zero, is called the yield stress of the fluid. Now, mathematically, it shows a difference in the graph, and it shows a difference in the equation that represents the fluid in this manner. So in Newtonian fluid, you have a non-zero y-intercept, sorry, a zero y-intercept, and for fluid like concrete, which we call as Bingham fluid, you have a non-zero y-intercept, which then is due to the presence of yield stress. But what is the physical significance of having an yield stress? The physical significance is that particular shear stress level has to be exceeded in the material for it to behave like a liquid. So until a particular stress level is not exceeded, it behaves like a solid. And once that particular stress level is exceeded, it starts to flow, and the resistance to flow will depend on the viscosity of the fluid, which will be the slope of this graph, which is eta in this equation here. And there are many, not just concrete, there are many fluids that you see in daily life that belongs to this category. For example, toothpaste is an example. If you apply a very small force on the when you put out the toothpaste, you might notice that it doesn't come out. But when particular stress is exceeded, it starts to flow. The same if you do with curd, ketchup, all these belong to the category of Bingham fluids or yield stress fluids. So yield stress essentially is the minimum stress that is required to initiate the flow. And then once the flow is initiated, the resistance to flow then depends on its viscosity. So now going back to this question of how we utilize concrete in 3D printing, the idea is to design concrete with very high yield stress. So if you look at conventional concrete, they are usually having an yield stress in the range of 200 or 100 Pascal, something a relatively low value as compared to 3D printable concrete. A 3D printable concrete would have something more closer to 2000 Pascals. So an order of magnitude higher than what you would have with conventional concrete. But because its yield stress is so high, when it's exited from the pipe, it's able to retain its shape. And to make this material to pump, to make this high yield stress material to pump, we use specially designed pumps that can work, that is able to pump this high yield stress fluid. And then once it's deposited, once it's free of stress, it's able to retain its shape. And that is the idea that we utilize in concrete 3D printing, to design it for very high yield stress. And also, when you design printable concrete, high yield stress is beneficial for buildability. But then the viscosity, if you can make it as low as possible, it would help in reducing the pumping pressure. Now, again, as I said, one of the other parameter that we need to look at is the fact that you can pump the concrete to the print head or the nozzle. So how can you pump this high yield stress concrete to the nozzle? So here we also need to understand a few basic characteristics about the pipe flow behavior, some of which you would already know from the basic fluid mechanics. For example, this is the velocity profile, the parabolic velocity profile that you would see with a Newtonian fluid. If you pump, say, water through a pipe, and if you plot its velocity profile, you can see that this velocity profile is like this. This is what we call as the Hagen-Poiseuille equation, which you must have seen in your basic fluid mechanics course. And if you see the how the shear stress is varying, the shear stress is minimum at the center, and the shear stress becomes maximum towards the outer edges. Now, if you do the same analysis in the case of a Bingham plastic material or yield stress fluid, you would see that it follows a parabolic profile initially, as you see here, and then towards the towards the center, you see a plug forming like this. So you see a parabolic profile, and then you see a plug forming at the center. This again becomes very clear if you look at the shear stress diagram again. If you see the shear stress diagram, it looks quite similar to this. What you would see that the shear stress is maximum towards the edges, and then it starts to decrease as you proceed towards the center of the pipe. Now, if the shear stress drops below the yield stress, if you go back here, below a particular stress level, it doesn't flow, it behaves like a solid. So when the shear stress is reached, so let's say that the stress level at this point reaches the shear stress, then below this point here, it behaves like a solid. So you see more of a rigid body translation of the material below the point where the shear stress decreases to less than its yield stress. So you see a rigid body translation in the region where there's lower stress level lower than its yield stress. And towards the outer edges of the pipe, you see shearing occurring. And as a result of that, you see that a parabolic profile more closer to what you associate with Newtonian fluid is seen. Now, this velocity profile or the pressure required to pump this fluid at a particular velocity can be obtained by using something called the Buckingham-Reiner equation. So if you look at this equation will involve the yield stress and both the viscosity of the fluid. So once you know these parameters, you can substitute in this to obtain the likely pumping pressure. And then this information we can use in the design of the pumping system. But now, when you talk about concrete, there's one more complication that arises, which is the formation of a lubricating layer. This Buckingham-Reiner equation is a general equation that's valid for all Bingham fluids, all yield stress fluids. So if you're doing this analysis, say with toothpaste, you will get a very good result. In fact, if you experimentally measure the pressure, and if you do the theoretical calculation for the equation, you'll see that you get a very close match. But if you do it with concrete, you will see that the Buckingham-Reiner equation gives a very much higher value than what is experimentally observed. Say, for example, if you get 10 bar with when you do it experimentally, if you do it with concrete, and if you measure the pressure as 10 bar, when you substitute in this, you might get values as high as 30 or 40 bar, several times higher. So the reason or why this happens is because the Buckingham-Reiner equation doesn't consider the formation of a lubricating layer that happens in the case of suspensions like concrete. So when you try to pump a fluid like concrete, what happens is that some liquid phase in the concrete can separate out under the shearing action and form a thin layer like this, as you see here. So thin layer occurs on the pipe edge, and this thin layer also will become sheared. And then within this thin layer of the lubricating layer, the bulk concrete is sheared. And then the shearing of the bulk concrete, once the stress level goes below its yield stress, you see the plug occurring at the center. So instead of analyzing as a homogeneous fluid, we need to analyze it as a heterogeneous fluid. A heterogeneous fluid, in fact, consisting of two Bingham fluid itself, a Bingham fluid of the bulk concrete, a Bingham fluid of the consisting of the lubricating layer. And this heterogeneous fluid has to be analyzed to make realistic assessment of pumping pressure. So once the lubricating layer effect is taken into account, sufficiently fair estimate of the pumping pressure can be made. I'm not going into the mathematical detail of how this can be done, but this is an important or something that can create a significant error in your calculation if this is not taken into account. Regarding pumping, one more thing that we need to look at, especially if you're using a piston pump, is sometimes too much phase separation can happen, and this too much phase separation can cause all the liquid to separate out from the concrete, leaving a very thick, unextrudable mass of concrete in the pipe. This is something that can happen sometimes. So it's also important to understand how we can assess this phase separation tendency of the concrete. So one way we can do that is by using an experimental setup which was used in my PhD, shown here. So we take a small sample of the concrete, and then we put it in this small sample, and a filter is placed at the bottom. And the filter, the grain size of the filter is such that it's around 2 microns, so all the granular materials is left behind, and only the water can pass through the filter. And then a compressed air is used, and then that is used to apply pressure on the top. And then we see that how much water is coming out at different time intervals. So using this, the water coming out at, or the column of water that forms at different time intervals, a parameter called desorptivity can be obtained, which can be related to phase separation. Now, one thing that you should note here, particularly with phase separation, is that it's not just the amount of pressure that you apply that dictates the amount of water that comes out during this test. So if you apply a high pressure, you will see maybe a higher amount of water coming out. But then it also depends on the duration for which you're doing this test. If you apply pressure for a longer time, you see that initially a small amount of water comes out, but as soon as some critical time is exceeded, more amount of water starts coming out from the concrete. So the amount of time for which the concrete is subjected to this pressure is also critical. Now, this is something that we need to again take into consideration, especially if you're using a piston pump. If you're using a piston pump, how the concrete is pumped is you have all the concrete placed in a large piston, and then the piston is slowly moved to cause the concrete to flow through the pipe. But then all the concrete that's placed inside the piston is being pressurized for a very long time, because the piston is very long and it's moving at a very slow rate. So the fact that you're applying this pressure for a long time creates too much water drainage and can leave an unextrudable mass in the piston. But on the other hand, if you're working with a screw pump, you are doing a continuous batching. You have a rotating screw, and then you feed the material into the rotating screw, and as soon as the material is fed, it's transported to the print head, which will take around only maybe some, depending on your pipe length, but typically less than 1 minute. So there is this pressure that you're applying is for a very short time for this case. But on the other hand, for the piston pump, you have all the material placed at once inside the piston, and then the pressure is being applied, and the entire extrusion time can be even as long as, depending on the length of the piston, can be even as long as 15 or even up to 30 minutes. So there's a significant time difference here. So this desorptivity analysis can characterize both the effect of time as well as the effect of the increments in pressure. That's one usefulness with this test procedure that I show here. Now, so far we talked about how to extrude the material, or the pumping requirements for the printable concrete. So what kind of analysis is required so that we can transport the concrete, which is placed which is once it's batched, how can you transport the concrete up to the print head? Now, once the concrete is deposited from the nozzle, we need to look at what are the criteria that can dictate the failure of the printed structure, especially the fresh 3D printed structure. Now, for the fresh 3D printed structure, you can have two types of collapse mechanisms. One is a plastic collapse, and the other is a buckling type of collapse. So I will look at both of this in detail. A plastic collapse happens when the weight on the bottom layer becomes too much and flow is initiated in the bottom layer. So as more and more layers are built on top of it, there's more shear stress exerted on the bottom layer. And this, once it exceeds the yield stress, the material would start to flow, as you can see in this image here. This The other type of failure, especially that you associate with slender elements, if you make very thin, architecturally appealing elements, you can also sometimes get a failure from geometrical instability, such as a self-buckling failure. So you can see that here, as the structure is being built up, you see a lateral instability occurring in the material, and then this causes it to buckle, and the material fails by buckling. And if you look at your strength of material, as you would have learned in your strength of material course, when you look at equations that can assess the critical buckling load, it will involve the material parameter elastic modulus. So it's not the strength of the material, it's the elastic modulus that dictates the tendency of the material to buckle. So you require two parameters essentially to decide if the material would cause sprint failure or not. One is the amount of stress that it can withstand, or let's say the compressive strength of the fresh material. The other is what is the modulus value of the fresh material. How much is the modulus value, so that if you have a given print geometry and if you're doing it at a particular speed, then is this modulus sufficient to prevent the failure of the material? So both these parameters needs to be characterized. One more aspect that we need to we need to keep in mind is both these parameters, both the compressive strength or the yield stress, let's say, and as well as the elastic modulus, both of this increases with respect to time. This is because there's cement hydration occurring in the material. This causes rigid network connections within the fresh cement base, within the fresh concrete. This would cause an evolution of these material parameters. So the rate at which you're printing must be in sync with the evolution of these material parameters. For example, if you have a mixture that has a very rapid evolution of these material parameters, then you can print quite fast because you are increasing the load on the bottom layer, but at the same time the bottom layer's material parameters are also increasing at a quite rapid rate. But on the other hand, if you're printing with a material that doesn't evolve sufficiently fast enough, then you may need to slow down your rate of printing. So we need to characterize these material parameters, which is the strength the material can have, as well as the modulus values. And then we also need to know the rate of evolution of these material parameters. How does these material parameters change with respect to time? Both these data is required for us to design the print process. So how can we do that? One of the ways we can do that is to do a uniaxial compression test on fresh concrete. So this is illustrated here. So so in this setup, we have a cylindrical specimen which is immediately demolded. So this is freshly cast and then it's immediately demolded. The cylinder can retain its shape because the 3D printable concrete is stiff, unlike conventional concrete, and therefore it's able to retain its shape. And then it's placed in a video extensometer system like this, and both longitudinal as well as lateral displacement is characterized by using the video extensometer system. Here, I should point out that the lateral displacement characterization is required because unlike hardened concrete, a lot of lateral deformation occurs in the material. So if you need to characterize stress, you need to use an updated cross-sectional area to convert force to stress. Because of the large lateral deformation, if you use the original cross-sectional area, you will not get a realistic estimate of the stress value. So here we see stress versus displacement values obtained at different time intervals, 0 minutes, 60 minutes, 180 minutes. So the maximum value obtained here can be used to obtain the compressive strength at different time intervals. Then plotting that with respect to time gives the evolution of the compressive strength. And the slope of these graphs, the slope of these different graphs can be used to obtain the elastic modulus. So this is stress displacement. But then if you know the original length of the specimen, from the original length of the specimen, this can be converted to stress strain graph. And from that, the elastic modulus can be obtained. It must also be shown how the failure modes differ in the material with respect to age. So if you see the early age material, you see that the material just fails by barreling. So it resists the applied load for some time and then it starts to flow out or barrel undergo indefinite plastic deformation, as you see here. And this is also very typical in the material behavior that we characterize. We see an elastic response, and then we see an indefinite plastic deformation occurring in the material. But then as the material hardens, some rigid connections are formed, and this breaking of these rigid connections causes a shear crack formation, which is more closely resembling to what we see with hardened concrete. We see shear cracks forming, and then we see in the material response also, as the shear crack forms, you see a softening branch forming, which is again more typical with hardened concrete. So you see an evolution from from an elastoplastic type material response to a strain softening type response, and this can be quite well captured from this test method. Yeah, and now just to give a few words on the mix design as well. So for the, as you could imagine, there's no standardized codes or procedures for designing printable concrete. But one of the ways we could try to do this is by using the particle packing approach. Using the particle packing approach, the granular skeleton can be designed. But then when you design the granular skeleton, we need to make a choice of different mineral admixtures. But again, unlike conventional concrete, a key parameter that we have to keep in mind is how these mineral admixture might influence your early age behavior. Early age, especially in terms of how quickly the material starts to set, how it influences the yield stress, how it influences the viscosity. This is something that we have to keep in mind. Say, for example, if you're adding, say, microsilica can really allow for a very fast evolution of compressive strength and elastic modulus because of its reduction in setting time. So then this means that if you use this kind of admixtures, you can have a much faster printing rate as compared to when you don't use microsilica. So the choice of mineral admixture also quite links with the type of print process that you want to have. And then, as I said, if phase separation is a problem, especially with especially if you're using a piston-based system, as we discussed earlier, the use of methyl cellulose can be a good approach. Robustness is also a key element that we need to keep in mind. So that means a batch variability in design. If you have a small variability in the cement batch, it should not cause a huge change in the properties of the material. So this is some aspects that we need to keep in mind when we look at the mixed design for printable concrete. So just to summarize the early age behavior, so I did this more in detail because this is one of the key aspects of concrete 3D printing. One is that before deposition and after deposition, you have different material requirements to be satisfied. Before deposition, we need to look at the pumping behavior of the printable concrete. For that, we discussed how it varies from a Newtonian fluid, how Bingham fluid has to be analyzed, and how the velocity profile will differ. And even when we analyze it as a Bingham fluid, we see a huge discrepancy in the predicted and experimentally observed value. This is because the fact that we don't account for lubricating layer properties. If you do account for lubricating layer properties, pair estimates can be made. And from these pair estimates, the type of pumping system required for use in 3D printing can be designed. Once it's deposited from the nozzle, we need to understand how failure can happen. One is the plastic collapse that we talked about, and the other is the collapse occurring from elastic buckling. So what are the material parameters that is linked to these types of collapse mechanisms? And then what are the parameters that we need to assess, and how we need to assess these material parameters with at different time intervals to design a print process. One more thing that we need to point out is the conflicting requirement before and after deposition. So for before deposition requirement, the material should be as flowable as you can make it. As much more flowable the material is, the more easier it is to pump the concrete. But once it's deposited, the yield stress should be as high as possible so that it can you can print rather very fast. So to address this conflicting requirement, one of the ways to do that is to introduce an accelerator at the nozzle, then have a small mixing unit at the nozzle. So this is also being used by several research groups now. So accelerator is introduced at the nozzle, and then that introduction of accelerator causes a very rapid evolution of elastic modulus and yield stress, allowing you to make very large, relatively larger structures at much more faster print speeds. Yeah, now we also briefly talk about the mechanical behavior of printable concrete. One of the problems with printable concrete when we do, let's say, a compression test is its anisotropic behavior. So if you test in different directions, you will get different compression strength values. So this is something that we have to accommodate in design. For example, if you are testing in this direction, and let's say if your layers are oriented parallel to the loading direction, and if it's oriented perpendicular, then you might see a different strength value for both these cases. Now, to understand this, you need to look at how failure of concrete happens in compression, which is depicted in this figure here. If you apply a compression load on the concrete in this, let's say in the vertical direction, then due to the Poisson effect, the concrete starts bulging laterally, and this bulging causes vertical cracks forming like this. So you see cracks forming like this, and then the restraint from the loading frame at the top causes these cracks to diverge outwards like this. So if you have an interlayer existing like this in parallel to the loading direction, so if you have an interlayer like this, it's more easier for the concrete to bulge out and move out laterally. And therefore, you would see a more premature failure when you have a loading, when you have the layers aligned in this direction. On the other hand, if the layers are aligned in this direction, you don't have an interface like this that allows an easy lateral movement or easy bulging out of the concrete. So because of that, you see a relatively higher compressive strength when you load it in this direction. This you also see with the anisotropic behavior. You also see in flexural loading. For example, if you have beams cut out, say from 2 and 3 directions, and you also have a vertical beam, you would see different flexural strength obtained for both these cases. Now, this again is very clear if you look at where the peak stresses are occurring. Let's say if you have this beam 3 here, and then if you're doing a single point bending test, you will have the maximum bending moment at this point here, and the maximum the bending moment in this section here, and the maximum bending stress occurring at the extreme fiber here. But if you consider the same situation here, if you have a central loading like this, then if you have maximum bending stress occurring here, then you have a crack existing here, and there's tensile stress existing in this direction. So this means that it's more easier for the concrete to move out or to break under this tensile stress. So you see a much more premature failure in the vertical beam. So you see, in fact, if you do the test, we often see that there's about 40% decrease in this direction as compared to directions 2 and 3. Directions 2 and 3 give comparable results to mold cast sample. That means if you make the same concrete in a mold and test it without any presence of any layers, you see that the strength is similar for 2 and 3, similar to the mold cast. In this one, you will see around a 40% decrease in strength. Sometimes you also get problems with using certain type of nozzles. For example, if you use a square nozzle, a small porous region can exist at the center, as you see here. And then this porous region can contribute to a lower compression and even tensile strength. So how do you characterize the interface properties? Because interface properties can, as we see in the earlier slides, can significantly influence the mechanical behavior. So one way to do that is to do a bond shear test. So you can cut out, for example, you can cut out cylindrical specimens with the bond at the center, with the bond existing at the center. And then if you do a direct shear like this, pulled from both directions like this, and cause a failure to happen at the interlayer, you can characterize the shear strength at the interlayer. Then if you do that on a specimen without the presence of interlayer, so suppose you drill the same size specimen, same size core from a mold cast concrete without any interlayer, you see that when you compare the shear strength values for both, you see around 20 to 25% decrease. So this level of decrease can characterize the interface properties of the printed concrete. One more key element that we need to keep in mind is that the bond strength can depend also on the process parameters. Say, for example, the time gap between layers. If you print with longer time gap, it has been observed that the interlayer strength tends to decrease and the mechanical properties tend to decrease because of the larger interlayer time gap. The speed with which you're printing, if you print at larger speed, also sometimes we see that it can influence the mechanical properties. In fact, decrease the interlayer bond strength. And another element is the height from which you're depositing the nozzle, depositing the concrete. So if, say, as this height increases, the height from which you're depositing increases, there's less push on the bottom layer, and you see a reduced interlayer performance. Yeah, and then before we wind up this section, it's one of the many questions that when we look at 3D printing, one of the questions that we often ask is, how do we make reinforced concrete? We can 3D print concrete from the different, from as various research groups have shown, but can we 3D print reinforcement along with that? Well, this is again a research question that needs to be answered, but there are been some reinforcement concepts that has been proposed. One is to use cable reinforcement, an unorthodox type of reinforcement, as you see here, and the cable is introduced in the layers, as you can see here. But the problem with this is, if you go back, this will reinforce in this direction. But as I mentioned earlier, it's the tensile strength is significantly lower in this direction. You do not still have any improvement in this direction because the reinforcement is going like this. So the bridging between the layer is not really happening from this kind of reinforcement strategy, although it can be automated. Another promising approach is the mesh and nail reinforcement concept. So different meshing and nail reinforcements has been talked about in some research papers. So here you can see different arrangements of nails. This allows you to create a bridge between the interlayer, the nailing. And for the meshing, what happens is that the mesh is embedded with some overhang like this. And this overhang embeds into the top layer. And this creates a bridging between the two layers. But again, introducing this in an automating these reinforcement techniques is again something that we need to look at. We need to further work on. The more common 3D printed reinforcement strategy has been to do a post-tensioning. As you see here, this is a post-tensioned bridge made in Netherlands. So the concrete is 3D printed, different smaller elements are 3D printed, and then a post-tensioning cable is inserted, and because of the post-tensioning, you have a more compression-only structure in the end. There has been also talk of external reinforcement. So, for example, this truss arrangement that you see here, the truss elements which are under tension have been externally reinforced, as you can see in this image here. So this is also one of the concepts that's been looked upon as how we can make reinforced or structures that can carry tensile stresses using concrete 3D printing. The other method that has been demonstrated or that we can look at is to look at compression-only structures. For example, a Nubian vault or a dome structure. In fact, if you look at how concrete structures have evolved, if you look at times before the reinforced concrete, especially the historic monuments, many of them utilize domes and arch shapes in regions where you need to carry tensile stresses if you go for linear elements. So this is one of the techniques that can be used, and because the fact that you don't require a formwork, these elements can be more or less made quite easily in concrete 3D printing. So now finally I also just talk a little bit about the long-term performance for concrete 3D printing before we move into the sustainability aspects. We do not have too much literature on concrete, on the long-term performance of printed concrete, because this being a relatively new technology. But some of the publications, particularly on post-structure assessment, has indicated that a higher porosity can exist at the interlayer. For example, this is a tomography image by one of our students here. So you can see that there's elongated pores at the interlayer, particularly when you print with longer time gaps. So if you print very fast without a time gap, we do not see a problem with this. But then when we have a time gap of 10 minutes or even higher, we see that there is a lack of, there's not enough hydrates formed here to segment the pores that occurs at the interlayer. Based on this, some hypothesis has also been made. For example, if you look at this publication, if you see how ions transport through these pores, because ionic transport dictates, let's say, a chloride migration or carbonate, how carbon dioxide ingress proceeds in the concrete, that can dictate many of the occurrence of many of the durability issues in concrete. Let's even fluoride induced corrosion or even carbon dioxide induced corrosion. So how ionic transport occurs is also something that we need to look at. So because of if you have elements with larger time gaps, as you show here, what could possibly happen is that larger ionic movement can occur through the interlayer, as you see in these images here. This usually happens through capillary absorption. But on the region of the bulk concrete where there's no interlayer, you see this is an exaggerated image, but you can see that there's much lower ingress of ions through capillary absorption. But on the other hand, large amount of capillary absorption can occur through the interlayer. But after that, once the interlayer may have become sufficiently saturated, then further progress then can occur inwards by diffusion. So initially, a small a layer is formed through capillary absorption, and then further ingress can occur through diffusion of these ions into the concrete. But then this is a hypothesis or a possible scenario that may exist based on the published literature that was presented in this work. But further studies on this is required to really know what will be the likely service life that you get with 3D printed structures. One other critical problem that we need to also point out with printed structure is shrinkage. Now, printed concrete doesn't have coarse aggregate most of the time. That means you often have a high binder content. The high binder content makes it a very good candidate for shrinkage cracking. So this is also something that we need to look at. But again, there's not that much of literature on shrinkage cracking potential of printed concrete. Initially, for normal concrete, the formwork protects the concrete from the external environment. So it's not exposed immediately to the external environment. But the fact that the concrete is immediately exposed to environment, external environment, can cause higher early age shrinkage cracking in printable concrete, may cause higher early age shrinkage cracking in printable concrete. Then the reduced bleeding, high fines content, all this makes it sufficiently more susceptible again. The other area is the use of slender elements. Again, when you make these architectural elements, you use elements which are very slender with high surface area to volume ratio. This again is a factor that can contribute to shrinkage. And the use of many chemical admixtures like silica fume, which I mentioned earlier, which could be beneficial for 3D printing. But then that can also sometimes lead to increased capillary pressure. So when shrinkage occurs, higher capillary pressure has been found to occur in silica fume concrete as compared to conventional concrete. So these are some of the challenges or some of the research needs that we need to look at when we need to for making realistic assessment of the long-term performance of printable concrete. Now we go into the next part of this presentation, which is the main essence. Having understood what is concrete 3D printing and what are the different material requirements at early age, how the mechanical behavior differs from conventional concrete, and then likely long-term performance of printable concrete as well. Now, can we, with this, using this information, now can we look at, or can we really see if concrete 3D printing is sustainable or not? Now, for sustainability assessment, firstly, we need to look at how we define sustainability. So sustainability, as often we see, is not just about using a greener material. So being environmental friendly is one of the pillars of sustainability. But there are two other pillars also that we need to look at. We need to have a structure that's socially acceptable. Then we also need to do this in a cost-effective manner. So not just being environmental friendly, we need to have we need to make a structure that's socially acceptable, and then we also need to have a structure that can be made with a reduced cost for it to be called as sustainable. Now, socially acceptable, if you see, especially with 3D printing, because of the unique architectural, because of the architectural freedom, as well as the possibilities with 3D printing, most of the time we meet this criteria of being socially acceptable. And also here we need to also mention that there's a reduced labor requirement for 3D printing. So less physical labor is required to make the structure. So all of this makes 3D printing is likely to make concrete 3D printing more socially acceptable. But then the real question is it really environment friendly and is it really economical? So this is something that we would look to answer in the coming slides. Now, especially regarding environmental and considering the economic aspects, we we will need to look at some of the key factors that can influence this. One is the unit material cost. So if you're going to make a structure with a given type of concrete, let's say 3D printable concrete, what is the unit cost of that concrete? So per meter cube of concrete that you're going to use, what is the cost that you're likely to, the cost that you're having to spend? The other is the amount of material that you're going to use. So if you can make the same structure with a reduced material volume or a reduced material quantity, then even though the cost is high, the unit cost is high, but you're using a reduced material volume, even then it still can be sustainable. So we need to look at not just the unit cost of the material, what is the total material that we are likely to use in making a particular structure. Then the last thing we need to look at is the service life of the structure. So once we have the structure built, for how long it's going to last, or do we have to make because if for example, if it doesn't have a very good long-term performance, then you end up spending a lot of money for repair and money as well as using more material in repairing and retrofitting the material. So three factors we need to look at. One is the unit cost of the material. The other is how much of the material that we're going to use in making the structure. And then we need to also look at what is how long the structure that we build is likely to last. So here, before one more thing that we need to keep in mind is the challenges in making a particular material selection. This is illustrated in this figure here. One of the key challenge in making a material selection is the interlink that exists between material function, shape, and process. So one is the function that the structure has to satisfy. That means the structural load that it has to carry, the durability or the long-term performance that it has to meet. Then the structure should have a specific shape as specified by the designer, or the shape, if you can, or a material efficient shape. Then this structure or the shape that you're going to make using this material needs to be made using a particular process. The problem with material selection is that all of these aspects are interlinked with each other. So you choose a material, but if you choose a material that doesn't meet the required function or cannot be cast into a particular shape, then you really cannot use that material. The same, for example, if you make a very architecturally pleasing element, you can design that element, but the problem is the formwork that you need to make, customized formwork that you may need to have for the structure, and this then creates problem. So all of these factors that we look at are interlinked with each other. Now the advanced design tools, like if you look at the advances in CAD and design softwares, if you see, these advancements now really allow us to design very optimized shapes. By using these optimized shapes, the same load can be carried with lesser material volume because of the fact that you're using a more optimized shape with a higher, let's say, if you're going to make a beam, for example, you use a rectangular beam, it can carry a particular amount of load. But if you use an I-section beam, the I-section beam has a higher I value, moment of inertia value. And because it has a higher I value, let's say if you're keeping the bending moment as the primary criteria, it has a higher I value, then the same load can be carried now with the reduced material volume. So using this idea, you can optimize, using this concept, you can have optimized shape. And the fact that you use optimized shapes allow you to reduce the total material usage. Now, this is where 3D printing really comes in, because 3D printing eliminates formwork, thus more material efficient and more sustainable shapes become more of a reality. This becomes more clear in this image here, if you see. Now, this is how the unit cost varies with complexity. If you have a structure which is made relatively less complex, let's say a rectangular beam or normal structure with where easy or conventional formwork can be used, its cost is somewhere going to be here. But then as you make it more and more complex with conventional concrete, your cost is going to be shooting up to significantly. This is because you're having to spend a lot of amount of money for making the customized formwork. And if you see the bold line here, this shows the market value. So the market value is high for less complex structures, but as you make it more complex, trying to make it more material efficient, you end up reducing the market value because of the fact that you spent a lot of money for the customized formwork. But if you look at digital fabrication, or 3D printable construction, which is shown by the dotted line here, it starts with a higher unit cost because the binder content used with printable concrete is much higher. So the unit cost is higher for the printed concrete. But then as you increase the complexity, unlike the conventional construction, you don't see that it doesn't exponentially increase in the same manner as is in the case of conventional concrete. So then you have a break-even point, and beyond this break-even point, you have a situation where the digital fabrication is really economical. So if you have a structure that's fairly complex, which lies in this region, you have a situation where the 3D printable concrete is, in fact, the unit cost itself of the structure can be more economical. The same exists in the case of market value. The market value is lower compared to conventional structure initially for printed concrete, but then as you increase it, as you increase the complexity, unlike the conventional concrete which starts to dip, the market value starts to dip. You see that it remains fairly constant, and only when you reach sufficiently large complex structures, you see a dip in the market value. So this also points out where the research direction has to go in terms of 3D printing. The research direction has to be to move this curve more towards the bottom, so that the unit cost can be reduced. So if, for example, if this curve can be shifted to here, so if you can have, having understood the material requirements for concrete 3D printing, if you can design these mixes more economically, then you start with a lower unit cost, and therefore you reach a break-even point much earlier than before. So even for relatively less complex structures, you can make 3D printing economical. And how this can be really executed is, this is one of the structures made in our lab. This is a 3D printed post-tension bridge, which is made by using topological optimization. So you can see the complexity level is fairly high in the structure. And I'll also just briefly discuss how the material volume reduction is happening here, how the efficient shape is being made here. So if you see here, this is the case of a rectangular beam subjected to a central point load, and if this is your actual material volume required, here you're providing material only in places where it's really high in demand. So here to carry the flexural stresses, here where the flexural stresses are high, these regions for the diagonal tension. So you can, on these regions, the material is provided high in volume, and the material in the other regions can be removed. This can be combined with a post-tension analysis, which was used here. So this is for a normal central point loaded beam. This can be combined with post-tension to achieve material volume reduction. So again, coming back to this graph, you make 3D printing economical when you introduce complexity in the structure, and then this allows you to have material volume reduction, as you can see here, if you compare these two, resulting in lesser use of the total material in making the actual structure. The other key point when you talk about especially sustainability is the potential for integrating different functionality. Especially in Europe, one of the key things that we look at is to have especially thermal comfort, especially because of the more extreme winters that we have here in Europe. As when we compare it with India, which has a tropical climate, thermal conductivity is also a key element that we need to consider in material design, in building design. So here, one of the research done by the research group of Richard Buswell shows how the thermal conductivity varies for printed panels and concrete block panels. Now, because of the complex shapes that can be made with printed panels, where air passage can be made available through these, if you make these complex shapes, these complex shaped panels have much lower thermal conductivity as compared to even the materials that we use conventionally. And the fact that you have a lower thermal conductivity for these printed panels, that means during the lifetime, during its lifetime, the building is going to use less energy, because a lot of energy goes into ensuring sufficient heating in the building. So if you have a material with lower thermal conductivity, and if you consider its lifespan, the building is going to use much lesser energy as compared to when it's made using the concrete block. So this is also an advantage that we need to look at. The other advantage also is the fact that you can make local composition control at the nozzle. So for example, if you have two print heads in the 3D printer, you can use one type of concrete for certain areas and another type of concrete for certain other areas. So you can have a monolithic structure with different material properties. Say, for example, if you go back to this situation, in these regions where there is high demand for higher structural performance, you can use a high strength concrete, and in the other regions, maybe we can use a lower strength concrete, which has a lower, which is more economical and has a lower binder content. So this is the fact that these function this local composition control can be integrated is also one of the ways that one of the significant advantages that's possible with 3D printing. And this can then, as I mentioned now, can be used to make functionally graded materials. Now, so far we talked about the cost or the economic side of sustainability. We also need to look at the environmental impact of 3D printable mixes. So here, this is a work by one of the PhD students in IIT Madras. So here we can see that he's compared the energy consumed for different binder systems per meter cube of per unit quantity of the different binders in terms of carbon dioxide emission and the energy consumed in making these binder. So what this allows is, this allows you to choose which binder is likely to be more environmental friendly. So here you can see that there's calcium sulfoaluminate cement, there's mixes with fly ash, silica fume fly ash blend, there's limestone calcine clay, which is also being talked of as a very green type of cement, different types of geopolymer concrete as well. And the energy consumed in making per meter cube of this material, and the carbon dioxide emission associated with per meter cube of this material is being shown in this figure here. So these type of analysis then allows us to choose which mixes are likely to create a lower environmental impact. So if you look at here, this is likely to create a lower environmental impact during its production stage. So that's important. Here we are talking about energy consumption and carbon emissions that occur during its production stage. So this then also points out the need for having a more comprehensive life cycle assessment. So if you go back for this figure that I showed here, this is until only the production stage. We don't know how each of these or how the service life is going to, what is the likely service life that you're going to get with these different binder systems. The same applies here as well for these structures. This is the cost reduction that you occur in the production stage, but during its life cycle, what is the likely cost that you're going to spend in repair and rehabilitating the structure? This is something that is unknown. So if you look at complete life cycle assessment, you have the material initially being made, which is the raw material, which is forms the cradle. Then this is transported and then pumped, which can be either offsite or on-site 3D printing. And then the construction facility is created. So this is where we have our gates. So we have the structure, the raw material being made, and finally the construction material structure being fabricated. Then what happens beyond that? What is the service life expected? Once you demolish these structures, how is there a possibility to recycle and reuse it? How are we going to dispose of this material? So these is, again, we don't have sufficient data on this right now to really say how much this is going to contribute or what impact the post construction impact of 3D printed structure. So a more comprehensive life cycle assessment is required really to make more realistic assessment of sustainability. So now with the different factors, aspects that we discussed, I'll kind of summarize this presentation. So we talked about construction by concrete 3D printing, why it's a really promising technology and why different groups around the world are looking at concrete 3D printing. Then we talked about the different material requirements. We discussed in detail about the early age material requirements, particularly. The early age requirement, there's before deposition requirement and after deposition requirement. The before deposition is essentially the pumping assessment and pumping characterization, where the fact that the lubricating layer is formed at the pipe wall interface has to be taken into account for making realistic assessment. Once it's pumped out, we need to consider what material parameters are linked with what type of failure, and how these parameters, compressive strength and elastic modulus of fresh concrete, can be characterized. In mechanical behavior, we talked about the problems with anisotropic behavior of a printed concrete. Then we talked about reinforcement strategies. But reinforcement strategy, we need a reinforcement strategy that provides tensile strength and ductility along all directions, not just along the print direction, but as well as provides a bridging between the different layers. The lack of data on long-term performance is a problem, especially if you want to have a more comprehensive sustainability assessment. So the post-structure assessment in some of the published literature indicates that the transport mechanism, the transport properties, particularly at the interlayer, are likely to be higher in printed concrete. Shrinkage assessment and mitigating strategies is something that we may need to look at if, again, when we look at the long-term performance of printed concrete. Then again, I go back to this graph really to, if you're somebody working on, if you're looking to work on concrete 3D printing or take up a PhD on concrete 3D printing, what are the real research needs that we need to look at? So again, I look back at this graph here. So now we are here where the cost is fairly high because of the introduction of the technology, and where the break-even point is only when you have sufficient complexity in the structure. But then through research, having more understanding on the material behavior, and then with this understanding, if we can bring down the cost of the digital fabrication techniques to some way here, then we have a situation where you have an application for concrete 3D printing for a more wider domain, even for relatively less complex structure. And to again show a comparison of the cost, the binder content essentially that we require in 3D printing, because the binder is the more cost-effective component in printed concrete. You see that it's relatively quite high for if you look at all these publications, they use relatively high printable concrete. But if you compare it with an M40 grade SCC, say for example, you can see where we stand here. It's about 50% higher when you compare it with conventional concrete. So the research in this direction, looking at optimize. So once we understand these aspects in more detail, can we work on strategies that look at more and develop more cost-effective printable concrete? This is a need for research. The others also the fact that we also need to look at if we can work with more environment friendly, cost-effective as well as more environmental friendly binder systems for 3D printable concrete. In fact, this is one of the main researches that we at Ghent University is involved in, developing more cost-effective binder systems using more environmental friendly binder compositions. Then the need for a comprehensive life cycle assessment. So for having a very complete and a more comprehensive life cycle assessment, we do not yet have data on the long-term performance or the transport properties or service life estimation. So research in that domain is required. What is the likely transport properties? How interlayer is likely to play a role in different durability issues. And once we have sufficient idea on that, we can make fair enough service life estimation, which then can be utilized in making a more comprehensive life cycle assessments. So this is our research group headed by Professor Hirdi Schutter and Kim. And you can see some of our printed elements that we made in our lab here in the background.